potential. Ohm's law states that at a given constant temperature, current I through a conductor between 2 points is directly proportional to the potential difference or voltage V across the 2 points. Thus, the ratio V to I is constant and is called the resistance R of the conductor. Consider a circuit with a battery, a rheostat, a key, an ammeter and a resistance wire connected in series. A voltmeter is connected in parallel to the resistance. Care is taken that the positive terminals of the ammeter and the voltmeter are connected to the positive terminal of the battery. The key is closed and the rheostat is adjusted such that the ammeter and the voltmeter show the minimum reading. The rheostat is then adjusted gradually, and the readings in the voltmeter and the ammeter are recorded at different instances in a tabular form as shown. Let the current passing through the circuit at any given time be I ampere and the potential difference across the resistance be V volt. The ratio of potential difference V to current I gives the value of resistance R in ohm. You will observe that the resistance is almost constant for different pairs of VI values. If you plot the values of V against I on a graph with V on the y-axis and I on the x-axis, it will be a straight line as shown here. This verifies Ohm's law. This graph is known as a VI graph. The slope of a VI graph can be determined by taking 2 points, P and Q, on the straight line. From points P and Q, draw normal lines to the x and y axis. Point C is the foot of the normal line from P to the x-axis, and point A the foot of the normal line from point P to the y-axis. Point D is the foot of the normal line from point Q to the x-axis, and point B the foot of the normal line from point Q to the y-axis. Distance AB represents delta V, or change in potential difference, while distance CD represents delta I, or change in current. The ratio delta V to delta I, which is also the slope of the VI graph, gives the resistance R of the conductor. The higher the slope of the VI graph, the higher is the resistance of a given conductor. Let us now consider the VI graphs of a conductor at 2 different temperatures, T1 and T2, where T1 is greater than T2. Thus, T2 is the temperature of the conductor before it is heated, and T1 after it is heated. The VI graph of the conductor after it is heated is steeper than its VI graph before heating. This is because, as the temperature rises, the resistance of the conductor increases. Conductors that obey Ohm's law are called ohmic conductors or linear resistors. For example, metals such as iron, silver, copper, etc., at constant temperature are ohmic conductors. For all ohmic conductors, the VI graph is a straight line, and the value of resistance R remains constant at a given temperature for any of the values of V or I. Conductors that do not obey Ohm's law are called non-ohmic conductors or non-linear resistors. Diodes and triodes are the best examples for non-ohmic conductors. For all non-ohmic conductors, the VI graph is a curve instead of a straight line. This indicates that resistance R of a non-ohmic conductor varies for different values of V or I values. To determine the resistance of a non-ohmic conductor at a particular value of V or I, draw a tangent at the desired point and find its slope. The resistance of a non-ohmic conductor is also known as dynamic resistance, since it varies for different values of V or I. Experimentally, it has been observed that the resistance of a conductor or wire depends on its length and area of cross-section. The resistance of a wire increases with an increase in its length, meaning that the resistance of a conductor is directly proportional to its length, L. Let this be equation 1. The resistance of a thick wire is less than that of a thin wire. The resistance of a conductor is inversely proportional to its cross-sectional area, A. Let this be equation 2. For a conductor of circular cross-section, the area of cross-section is equal to pi r square, where r is its radius. Hence, we can also write that the resistance of the conductor is inversely proportional to the square of its radius of cross-section. Combining equations 1 and 2, we get R is proportional to L by A. Replacing the proportionality symbol, we use a constant ρ, which represents the resistivity or specific resistance of the conductor. Now, we have R is equal to ρL by A. Let this be equation 3. From equation 3, we get ρ is equal to RA by L. If the length of a wire is 1 meter and its cross-sectional area is 1 square meter, then the resistivity ρ of the wire becomes equal to its resistance. Hence, resistivity ρ of a material is the resistance of a wire of that material of unit length and unit cross-sectional area. If the length and area are measured in meter and resistance is measured in ohm, then we get the unit of resistivity as ohm meter. The resistivity of a material depends on its nature and the temperature of the conductor. It is independent of the shape and size of the conductor. It is a property of the material of the conductor and does not depend on the potential difference applied across the conductor or the current through it. A good conductor has less resistivity, whereas a bad conductor or insulator has high resistivity. The resistivity of semiconductors lies between that of conductors and insulators. The resistivity, and therefore the resistance of a metallic conductor increases with an increase in its temperature, whereas the resistivity of a semiconductor decreases with an increase in its temperature. It is observed that the resistance of some materials like tin and lead decreases tremendously with a decrease in temperature in the very low temperature range of the order of absolute zero. Substances under this condition are called superconductors. The resistance of a superconductor is nearly zero at very low temperatures. The table here shows the resistivity of some materials. Another important property of a material that determines its ability to conduct electric current is conductivity. Conductivity, represented by the symbol sigma, is the reciprocal of resistivity. That is, sigma is equal to 1 by rho or L by Ra. Conductivity is measured in per ohm meter or Siemens per meter. Since conductivity is the reciprocal of resistivity, its unit is the reciprocal of ohm meter, that is, per ohm meter.